This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello and welcome back to the Neurosurgery Hub podcast. I'm Dr. Aris, senior attending here, and today we are diving into the intersection of artificial intelligence and clinical workflow management.
And I'm Dr. Alara. Today, we're looking at a fascinating new study from Scientific Reports, published in 2026, titled A Cost-Sensitive Multiclass Machine Learning Framework for Postoperative Neurosurgical Triage, or simply Neuro-TACTIC. This work comes out of the Heidelberg University Hospital and the German Cancer Research Center.
This is a timely paper, Alara. Every day after an elective craniotomy, we face the same dilemma. Where does this patient go? We have to balance early detection of a potential hematoma or cerebral edema against the very real constraints of staffing and bed availability. Traditionally, we've used our gut feeling or perhaps some binary risk scores.
Exactly. And the authors point out that most existing models are binary. It's either ICU or not ICU. But in modern neurosurgery, we have a three-tier system: the regular ward, the intermediate care unit, or IMC, and the intensive care unit, the ICU. The IMC is that crucial middle ground for patients who need closer monitoring that a ward can provide, but don't necessarily need full ICU support.
Right. And ignoring that middle tier in predictive modeling is a bit of an oversimplification. The other problem the authors mention is the asymmetric cost of triage. If we send someone to the ward who should have been in the ICU, that's a potentially catastrophic under-triage. If we send a stable patient to the ICU, that's an over-triage. It's expensive and uses a bed someone else might need, but the harm to the patient is different.
That's where the cost-sensitive part of Neuro-TACTIC comes in. They developed an XGBoost-based classifier using a retrospective cohort of 1,072 patients who underwent elective craniotomies. What makes this framework unique is a tunable parameter called zeta.
Let's break that down for the residents listening. Zeta isn't just a random Greek letter here. It's a way to integrate resource-related and harm-related costs. By adjusting zeta, a department head can actually tune the model to be more conservative or more resource-conscious, depending on their local staffing ratios or the specific definitions of ICU-level events in their hospital.
Precisely. It allows the model to shift its thresholds. The researchers used 27 features to train this. They looked at demographics, intraoperative data, and imaging-derived features.
27 features is a solid number, enough to be robust, but not so many that it becomes a black box that's impossible to interpret. What were the heavy hitters in terms of prediction?
They did a feature importance analysis, and the results are very relatable to what we see in the OR. The most influential predictors were operative duration, tumor volume, surgical position, body mass index, and patient age.
That makes perfect sense. A 10-hour surgery for a large skull-based tumor in the park bench position is a completely different physiological hit than a 2-hour convexity meningioma in a supine patient. The inclusion of tumor volume as an imaging-derived feature is also key. It's a direct proxy for the extent of potential cerebral edema and the complexity of the dissection.
And BMI is an interesting one. We know that higher BMI can complicate postoperative respiratory management and mobilization, which might nudge a patient toward a higher level of care, like an IMC.
Now, let's talk about the numbers. Machine learning often looks great on paper, but falls apart in the real world. How did Neuro-TACTIC hold up in testing?
They used repeated cross-validation and bootstrap analyses. In the development cohort, they achieved an average AUC, that's the area under the ROC curve, of 0.67 and a weighted F1 score of 0.49. They also tested it on an independent evaluation cohort of 81 patients to see how it generalized.
And?
The performance did drop slightly, as expected. The AUC was 0.66 and the weighted F1 was 0.44 in that independent group.
Those numbers might seem modest to a computer scientist, but for our listeners, it's important to remember the context. Predicting the human element and the variety of postoperative courses is incredibly difficult. A 0.67 AUC in a 3-class triage model, ward versus IMC versus ICU, is actually quite a feat, especially when you consider that most prior tools only tackled 2 classes and often lacked the ability to be tuned for cost.
I think the cost-sensitive aspect is the real meat of this paper. At their chosen operating point of zeta equals 0.975, the model demonstrated stable behavior. This zeta parameter acts as a dial. If you're in a hospital with very few ICU beds, you might dial it one way. If you're in a high-risk tertiary center where you absolutely cannot afford a single missed deteriorating patient on the ward, you dial it the other way.
It's moving away from one-size-fits-all AI. The authors are very clear that this is a methodological proof of concept.
It's not something you're going to download as an app tomorrow and start using to discharge patients.
Right. They emphasize that prospective validation and multi-center evaluation are required before clinical deployment. We need to see how this works in real time and across different surgical cultures.
Let's look deeper into the multi-class challenge. In the paper, they talk about how collapsing the decision into ICU versus non-ICU fails to account for the growing role of intermediate care units. Alara, in your experience as a fellow, how often do you see that middle patient, the one who is neurologically stable but had a long surgery and maybe some intraoperative blood loss?
Every day. And that's the patient who often gets stuck in a gray zone. They don't need a ventilator or pressors, which are typical ICU interventions, but you don't want them on a regular ward where the nurse-to-patient ratio might be 1 to 10. Neuro-TACTIC is trying to quantify that gray zone using the XG-Boost classifier.
And for the residents listening, XG-Boost is an ensemble learning method. It essentially builds a series of decision trees, each one trying to correct the errors of the previous one. By using 27 demographic and intraoperative features, it's looking at the gestalt of the patient in a way that a simple regression score might miss.
It's also interesting to note what they focused on: elective craniotomies. This isn't for the emergency trauma patient or the ruptured aneurysm. Those patients are almost always heading to the ICU. This is for the bread-and-butter neuro-oncology cases, where the triage decision is actually a choice.
Exactly. The paper highlights that many institutions default to routine ICU admission after elective craniotomy, even though we've known for years that only a subset of these patients actually require ICU-level interventions. That's a huge waste of resources.
And the opposite is true too. The paper mentions that insufficient monitoring risks delayed recognition of adverse events like hemorrhage or acute neurological decline. These things evolve rapidly in neurosurgery.
So, to summarize for our audience, Neuro-TACTIC is a framework that uses machine learning to sort patients into 3 buckets: ward, IMC, or ICU. It uses things like surgical duration, tumor volume, and patient age. And most importantly, it lets the hospital decide how much they value saving a bed versus preventing a late transfer to the ICU through that zeta parameter.
It's a very sophisticated way of looking at a problem we usually solve with a 3-minute conversation in the hallway. While the AUC of 0.66 to 0.67 shows we still have a way to go in terms of perfect prediction, it's a massive step forward in terms of methodology.
I agree. It's about building a framework that respects the complexity of our clinical environment. We aren't just looking for yes or no, we are looking for where and why.
It's a very sophisticated way of looking at a problem we usually solve with a 3-minute conversation in the hallway. While the AUC of 0.66 to 0.67 shows we still have a way to go in terms of perfect prediction, it's a massive step forward in terms of methodology.
I agree. It's about building a framework that respects the complexity of our clinical environment. We aren't just looking for yes or no, we are looking for where and why.
If you want to dive into the math behind the cost-sensitive framework or see the full list of those 27 features, the paper's in Scientific Reports, 2026. It's definitely worth a read for anyone interested in the future of surgical workflow.
Well, that's our time for today. Thank you, Alara, for walking us through Neuro-TACTIC.
Thanks, Dr. Aris. It's always great to see how AI is trying to tackle these logistical headaches in the OR.
To our listeners, thank you for joining us on the Neurosurgery Hub podcast. Stay sharp, and we'll see you in the next episode.
Goodbye, everyone.